In section 10.4, we're going to look at what is the central method for solving all trig equations for year 12 and year 13, the whole of the A-level. If we're going to solve an equation involving sine, cos or tan, or later on the other trig ratios that we'll learn about in year 2, then we're going to need to use the method from section 10.4. And often the tricky bit with trig equations is people don't realise that we're always trying to turn it into something that looks like this. Sine theta equals a constant, or cos theta equals a constant, or tan theta equals a constant. If your equation doesn't look like that, you need to make it look like that before you can solve the equation. The other part of the equation is this. Sine theta equals a constant. Well, if we look at the graph for sine theta, and this could apply to cos theta or tan theta, I'll just do the example for sine, that would look like this, right? And it keeps going in the negative direction as well. So if, firstly, the constant has to be a value between 1 and minus 1, otherwise I can't have sine theta equal to that constant. And say that constant was this number here, I don't know, 0.6 or something. Well, this value of theta here has a sine theta equals 0.6, so that would be a solution. So if this was sine theta equals 0.6, there would be a solution here. But this value of theta here, sine of that sine of that angle is also 0.6, and the same about this angle and this angle. So there's lots of solutions. So in order to deal with this, either we say, well, there are infinitely many solutions, and then we work out a way of writing those down, or we take the other option, which is the option we're going to take at A-level, which is this. We're going to put an interval there as well, which is often between 0 and 360 degrees. Oops, sorry. Theta is between 0 and 360 degrees. Sometimes it goes from minus 180 to 180, and sometimes the interval is different even to those things. But that is the typical trig equation question. If you can solve that, then you need to use it to solve any trig equation we're going to do. If you can't solve that, you can't solve any of the more difficult trig equations. So this is the important bit, okay? Now, you'll notice in the textbook they are using these cast diagrams, which I mentioned already I'm no great fan of, so I'm going to show you a method that doesn't need the cast diagrams, and it works like this. So we're going to solve this equation, sine theta equals a half, in this interval, 0 less than equal to theta less than equal to 360 degrees. And the way we do it is like this. First things first, we can say theta equals sine inverse of a half. And we could use a calculator, or we can remember that sine inverse of a half is 30 degrees. Okay? Now, the calculator solution, or the first solution that we get, we're going to call that our principal solution, or our principal value, okay? And that always comes from the calculator, or because it's a value of sine that we know. So if this is sine theta equals root 3 over 2, then I'd know the answer was 60 degrees. But I only know that because it happens to be one of my special ones. Almost always, that principal value will come from your calculator, okay? So now we've got the principal value. This is what we're going to do. We're going to draw ourselves a sine graph. And we're using the fact that this sine graph is completely symmetrical. Now, what I mean when I say it's completely symmetrical, first of all, let's just deal with this. The interval they're interested in 0 to 360, so we could draw the graph from 0 to 360. We could draw it a bit bigger than that as well if we wanted, but this is the bit that we're going to need. So what do I mean when I say I'm using the fact that this graph is completely symmetrical? Well, this is what I mean. I mean that this part of the graph here is exactly the same size and shape as this part of the graph here and this part of the graph here. Okay, so once you've got 90 degrees worth of sine graph, then the rest of the graph is made from flipping it around, turning it over, flipping it around and turning it over. But there's only one sort of shape here. It's this sort of shape, right? Once I've got that bit, this bit over here is the same, this bit here is the same, this bit here is the same. And that's the fact that we're going to use, okay? So this is how we're going to do it. I've taken an angle, it was 30 degrees, I put it into sine theta and I got a half. So if I put 30 degrees in, then my output is a half, okay? Now what I'm going to do is I'm going to draw a line across and I'm going to look, and I'm going to say, oh, well, look, this when the outputs are half, the input was 30 degrees. But another possible input was this number here. Another possible input was this number here. Another possible input was, all the other numbers, if I keep this graph going, this number here, this number here. So these are the solutions, okay? If the output was a half, the input was either 30 or this number or this number or this number or this number. Now the only ones we're interested in are between 0 and 360, so I can ignore all of these ones. So I've got 30 degrees, and then there's only one more solution, which is this one here. So what is that number there? Well, this height here is a half. This height here is the same height, so this is a height of a half. And because this part of the graph here and this part of the graph here are exactly symmetrical, this distance here and this distance here must be the same. Okay? So if that's 30 degrees, this must be 30 degrees. So this is 30 degrees away from 180. Okay? So in other words, 150 degrees. And there's my other solution. So my two solutions are 30 degrees and 150 degrees. What's important here is that you realise this is 30 degrees away from an x-axis crossing point. So this must be 30 degrees away from the x-axis crossing point. The mistake that some people make is to say, well, it's 30 degrees away, and then they measure 30 degrees away from the top of the graph. So they measure 30 degrees away from here and come up with an answer of 120 instead of 150. Okay, so that's what we've got to watch out for. So our answers are theta equals 30 degrees and 150 degrees in that interval. Okay. Now, there isn't really anything else in the next couple of examples. That's everything you need for 10D, but it's such a commonly used idea that I will do another example because it's one of those things that people do get confused by. I've done an example with a sine. Let's do an example with a cosine, just to make sure that we've kind of got the idea. If you want to stop it here and go on straight on to 10D, that's absolutely fine. I'd recommend it, in fact, if you're feeling confident. So let's have a look. Let's take that. So I said we'd do a cosine. So and I'm looking at exercise D, question 2, and we're given the question cos x equals 0.4. And in this question, it actually asks us just to find the principal solution. So in that case, we just say cos inverse of 0.4. So the principal solution to this equation, we go to the calculator, we say cos inverse of 0.4, and our answer comes out to be 66.4 degrees, okay? To three significant figures, it's 66.4 degrees. Now, what we need now is the second part of the question on 10D, where it doesn't say just give me the principal solution, it says what are the solutions for x is between 0 and 360 degrees. And the way we do that is this. We take a graph, it's this time a cosine graph, so we draw it starting at 1 and going like this. Make it no smaller than this. This is about as small as you can do it and still be able to draw everything you need on it. I've drawn it from 0 to 360 there. No harm in drawing it a bit bigger. And 66.4 degrees has a cosine of 0.4. So if I input 66.4, my output is 0.4. What I wanted to know is if I got the output of 0.4, what were the possible inputs? Well, one of the possible inputs is 66.4, but for this output here, I could have input this number here or this number here. I'm only interested in solutions between 0 and 360, so I can ignore this part of the graph and I can ignore this part of the graph. Only this answer I'm looking for here. This shape is exactly the same as this shape. I've drawn it a bit scruffily, it doesn't look the same, but that shouldn't stop us. This is 66.4 degrees away from the top of the curve. So this distance here must be 66.4, okay? Another way of thinking about that is that the gap between 66.4 and 90 is the same as the gap between 270 and this number that we're looking for here. Okay, so this is what I was saying, where the distance from the top of the curve to our angle is the same over here. There's the top of the curve, here's our angle. The distance from the x-axis crossing point to our angle is the same over here. Here's the x-axis crossing point, here's the angle we're looking for, okay? And sometimes these two distances get swapped round. That's why it's important that we sketch the graph clearly and we remember to use the symmetry as carefully as we can. So the way that I'd think of this is now that the solutions are x equals 66.4 and 360 take away 66.4. Oh, slightly pathetically, I can't think fast enough. What are we looking at? 290 4-ish. So yeah, 360 take away 66.4. My brain's not working fast enough to do the 0.4 bit and speak coherently at the same time. 293.6. Oh, how embarrassing. Well, I won't edit that out just to show that I can be stupid. As though I haven't shown that enough times. Right, that is the end of section 10.4.